Okay, so the game here is to derive the average power in a circuit, and we're going to derive the complex expression form. But to do that, first, we're going to consider the expression for the average power using just real functions. Then after that, we'll show that using the complex functions, we get the same answer. Okay, so to begin, we let the voltage be equal to some maximum voltage times cosine omega t, and we let the current be equal to some maximum current times cosine omega t minus theta. This allows the phase of the current to be different from the phase of the voltage, and that's the whole point of this exercise. So if we plug in these expressions for V and I, we get that the average power is 1 over the period, integrated from 0 to 1 period of cosine of the maximum voltage times cosine of omega t times the maximum current times cosine omega t minus theta dt. So rewriting that, we can pull out the Vm, the Im, so we'll have Vm Im over t, and there's the Vm Im over t. And we're going to use a trig ID. This expression has the product of two cosines. We want to put those together. So we use the trig identity cosine alpha, cosine beta equals 1/2 cosine alpha minus beta plus cosine alpha plus beta. And I forgot the closing brace, but it's there. And we're going to use this trig ID by setting alpha equal to omega t minus theta and beta equal to omega t. Now when we do that, I think I skipped a, yeah. When we do that, when we plug in our trig identity, here's the 1/2, right there's the 1/2 from the trig identity. There's my first term. That's alpha plus beta is omega t minus theta plus omega t. Alpha minus beta is omega t minus theta minus omega t, which just leaves the minus theta. And in the second term, we had alpha plus beta. So it's omega t minus theta plus omega t. So it's 2 omega t minus theta dt. Now if you look at this, this becomes two integrals. The first one is just cosine minus theta is a constant from 0 to t, so that just comes out of the integral. And the cosine 2 omega t minus theta integrated over one period of the function is going to integrate to 0. So you have the 1 over t here, and now you have the integral from 0 to t dt. That's just equal to t. And so the two t's cancel, and you're left with Vm Im over 2 cosine minus theta. So now the game is going to be to try to use the complex expressions for current and for voltage and show that we get the same result. So in the complex version, we let Vm become V maximum e to the j omega t, and we let I of t equal Im e to the j omega t minus theta. Those are the complex analogs. Now the claim is that the average power will be given by 1/2 the real part of V complex conjugate times I. So if we plug in our expressions for V and I and take the complex conjugate of V, we wind up with 1/2 Vm Im. These are just real numbers, so they pull out of this real brace expression thing. E to the j omega t for V becomes e to the minus j omega t, and the other exponential remains the same, e to the j omega t minus theta. And when you multiply e to the one thing times e to another thing, you just get e to the sum of the two things. So you're left with 1/2 Vm Im real part of e to the j minus theta. But the real part of that is just cosine minus theta. So this expression is the same expression as we got before when we used real functions. So we showed that using real functions, we get the same expression for the average power as we get using complex functions.